So the key elements in this talk are going to be the new functions astroposition and astrographics, which will be imitating what we have done in the geo framework. So we already have Astro functionality in Wolfram language. Functionality introduced by Jeff over the years, like things like moon position, sidereal time, etc. Also, we have large collections of data objects in the domains of stars, galaxies, etc. But we want to do something that is first-class citizen in Wolfram language rather than being Wolfram alpha based. So astroposition will be the main player. Astroposition packs an enormous amount of information about the solar system and beyond. And we will produce maps of a sky with astrographics, again, reusing very much of the geo framework. As with geo, we emphasize precision in computation, and here relativity will become important. We use modern data, in particular something called NASA kernels, which are lots of coefficients of the orbits of the planets. And so if you use this, it will start by downloading large files. And when I say large, I mean gigabytes. Right? So this needs to happen the first time for precise computation. This is the current Astro team. Jeff Bryan is handling all the data part, and he has the practical experience I don't have. And Truman from Ecuador is helping us connecting to the external collections of information, databases of Astro information. So this part, I will go very quickly through it because we already saw it. And I will go directly to astroposition. Then we will see some functions to perform computation, astrographic maps, and some examples. And finally, we will see some nice examples of constellations that Jeff has been working on. Okay, as we said this in the previous talk, in order to have precise computation, we need to have precise time systems and reference frames. There are 4 main families based on which plane we are basing them. And then once we have chosen a plane, the equator of the Earth, the ecliptic, the galactic plane, or the local horizon, we have to choose an x-axis that defines the whole frame. In relation to time, there are multiple choices of time system that we introduced, I think 1 year ago or 2. And the main time that we will be using in Astro is the terrestrial time system, which is atomic time measured at the surface of the Earth. In order to do some computations, like the motion of the planets, we have to change to something else, right? Because the planets do not care about what's happening at the surface of the Earth. Okay, so let's start playing with astroposition. The main idea is to imitate geoposition. So astroposition has 3 arguments, a bunch of coordinates, it can be an array, the frame, which is the equivalent of the datum. This is the physics part, and the coordinate system. The coordinate system can be things like Cartesian, cylindrical, right ascension declination, or it can be also a projection. For example, suppose that we want to observe the moon. By default, we will observe it from the local horizon frame. And so this is the azimuth, and this is the altitude. Note, I'm giving values to 0.1 second. If you're not familiar with angles, an arc second is about a coin at the distance of a mile, right? So it's precise. A milliarc second, which is more or less what I estimate this is precise to, is about the size of a person lying down on the moon. So that's the precision that we want to achieve. So now, this object contains inside the numbers. So this, you see, this is the azimuth, this is the altitude, this is the distance in astronomical units. So these will parse it into something more readable. And we store also the date of the observation and the location of the observation. This is some sort of metadata so that you can perform changes of coordinates, right? Because if you are observing from something that changes in time, you want to recall when the measurement was done. So we can change to other frames like the equatorial. In the equatorial frame, the coordinates are called right ascension and declination, the ecliptic frame. And notice that when we say equatorial, Astroposition is actually choosing one of these variants for you. You can say which one you want. You could say here meme instead of tete. But if you just say equatorial, it will choose one for you. Excellent. For example, we can also say, I want the coordinates in Cartesian coordinates, right? So now you get the X, Y, and Z coordinates of the moon from where we are. Okay. Something fun is to do dynamic computations, right? And so we see here how the moon is moving. Now, this motion is not actually due to the moon. It's mostly due to our rotation. If we want to look at the moon, how it's moving, really, we do this. We just call this from one of the frames that do not move with respect to the stars, right? And so we see how that motion is actually much slower. So let me remove this. So we can say extract as usual with methods, all the information that there is inside. And if you want this expressed nicely, the MS string will do that for you. Astroposition can also understand directions. For example, what's the zenith? The zenith is directly upwards. So that's azimuth is 0, altitude, this angle is exactly 90 degrees. Or we can say, what is the north celestial pole? That depends on our latitude, right? And this angle is effectively our latitude. And this angle, this is not 0 because of this misalignment between the celestial rotation axis of the Earth, the instantaneous rotation axis, and the geographic axis. There is a little bit of a difference. But if we want milli-arc-second precision, we have to take that into account. For example, this is the true equinox. We refer to this frame. Now, in this frame, the true equinox, this is true equator, true equinox. The true equinox is the direction of the x-axis, so that's totally 0. But if we go to some other frame, then we see that it has moved. This is the effect of precession, right? The ecliptic and the equator are moving, and so their intersection, which is the true equinox, is moving too. And so we compare with something that happened in year 2000, we see how much it has moved since then. And this is a consequence of nutation, right? So mean equinox means averaging for nutation. And so we see here a few arc seconds due to the nutation of the Earth. The axis of the Earth is wobbling with a period of about 18 years and an amplitude of about 10 arc seconds. Something fun is to observe ourselves from the moon. For example, this is the position of Mare Tranquillitatis, and we can say, where are we from this location, right? And so that's the azimuth and altitude of this position from a location in the moon, right? So with astroposition, we can observe anything from anywhere. Now, where are we with respect to the 0, 0 of the coordinates of the moon? Now, because the moon is always facing us, this point is always facing us. So from this point, the Earth is always up there continuously. But it's not always in the same place. So let's compute the position of some object from this place on the moon for any date. And here I have the D controlling the day, right? So if we plot this, and I'm cranking up the precision here, we get this plot over 2 months. So what is happening here? So again, we are observing Champagne from the moon. So what we see here are the so-called, and notice that the angle is 82 to 87. So this is the altitude. The Earth is always up there from this point in the moon, continuously, for a month, for 2 months, I mean, always. So what we see here are the so-called librations of the moon, right? Due to the ellipticity of the orbit. So The moon is not always exactly facing axis. It's moving a bit. This is the elevation. And then the superimposed oscillation is simply champagne going up, going around the Earth daily, right? So if we observe not champagne, but the center of the Earth, we get the same curve, but without the oscillations, right? And so if we subtract that, we get the complicated geometry of the combination of both things. Right? These computations contain a lot of information about the motion of the moon. Centers and barycenters. So when we imagine orbits of things around the sun, we think of them as being like very boring and flat, but they are not. So let's compute what the C, so we are going to be computing the C component of the Earth in the ecliptic frame. Remember, the ecliptic is the plane of the orbit of the Earth. So we would imagine that the C component with respect to that plane is kind of boring, flat, and doing nothing, but it's doing that. And this is over a period of a year. So there are two things here. One is this oscillation, which is monthly. It's due to the moon. The moon, when it's moving around the Earth, is pulling up and down the Earth. So we see here the effect. And then we have this seemingly impossible linear trend, right? And so what happens is that we are looking only at a very, so this is again, sorry, I should repeat again. So we can eliminate this oscillation just by looking not at the position of the Earth, but by looking at the position of the Earth barycenter, right? And so this is, now we are looking from the solar system barycenter. So what did I do here? So what I'm trying to introduce is, rather than looking at the Earth, we are going to be looking at the Earth moon barycenter, right? And by doing that is when we eliminate this oscillation here. And then we, yes. So what I wanted to say, sorry, I forgot, is that we can look at this by saying, rather than looking at only 1 year, let's look at 100 years. Right, and now what we see is this curve. And what we see here, we were looking only at a little bit of this. So what we see here is now the effect of the pull from the big planets, like Jupiter, right? Like something every 14 years, etc. So this is actually what the C component of the Earth with respect to the ecliptic plane is doing, you see, in kilometers. Right. So the Earth is going up and down like tens of thousands of kilometers over the years due to the pull of other objects in the.
Already takes out the moon.
No, these not yet. These would take out the moon. So if we zoom in this plot, we still see there the little oscillations. Here, we don't see them. This is by changing from the position of the Earth to the position of the Earth-Moon barycenter. Right? So the use of barycenters is important. I'm going to show here the same thing, but now with Jupiter. So this is the position of Jupiter with respect to the Jupiter barycenter, or vice versa. I'm actually computing the position of the barycenter of Jupiter with respect to Jupiter. Jupiter barycenter means the barycenter of Jupiter and all its moons. Right? And then this is doing something like this over a period of 100 days. So, not simple. All this information is in Astro position. You can compute, for example, distances. This is the distance from ourselves to the moon over a period of a month. This is something that happened recently, which is this is the distance from Jupiter to us. So it had a minimum very recently. We can find there 2022 point something. We can find the position of that minimum, and it turned out to be this, right? Very precisely measured. And we can compute, for example, also distances in space. These are angles. So this is the closest approach between Jupiter and Saturn. And again, this is what it's doing angularly over the years. And we had a minimum very recently too. Again, we can call this broke. Okay, sorry about that. Okay. So now let's talk about astrographics. So let's see. Okay. So this is what astrographics does by default. It's a map of the local sky. And here we see the following. There are many things here. This is our local horizon. Here we see north, south, east, west. They seem reversed, but you have to remember this is something that you are looking upwards, right? So here we see Polaris in the direction of north, and here we see the sun. It raised here, and it will move in this direction and then sets on the west. That's the moon. And here we see lots of stars. We have a catalog of about 100,000 stars to show in these maps. In the future, we'll have many more. So it's interesting to see this in a manipulate. So that's today from 0 hours to 24 hours. And so we see how the sky is moving. Let's show time. So at some point, the sun rises here at 7 something. It moves. That's up in the sky about midday. And then we continue. And then it sets. There are 4 planes here. The blue line is the ecliptic. The purple line is the equator of the Earth. And the brown line is the galactic plane, the 4 main families of planes that we were talking before. We can use other frames. And this is the equatorial frame showing the whole sky. We see the 4 main planes again. So the purple is the equatorial frame. We will add numbers and things to identify coordinates. That's the ecliptic frame by default, also shown in the equirectangular projection. And the galactic frame is typically used with the Molvide projection. So by default, this is going to choose the Molvide projection for the galactic plane. You can also choose your own projection. For example, this is a triple. You can, sorry, I want to make this bigger. You can add grid lines, astro grid lines. Here we are adding 2 sets, the galactic grid lines in brown, the horizontal grid lines in steps of 15 angular degrees, etc. Right? You see the sun, the position of the planets, main stars, etc. So this is changing quite a lot. The graphical details of this might change a lot in the future, but the information is there already. So we can also add a nice background containing the galaxy, right? That's that. That's an image produced by the Gaia project by combining the billion+ observations they have made. Right? So this is the equatorial plane, see the sun, etc. We can also use another projection like the Lambert azimuthal projection, right? And now we see again the full sky with the galaxy. You see that's our horizon. We see the sun here, you see? So it's day is this part, night is this part. right? So always look at where is the sun to decide which is day, which is night. Okay. Now, those were maps of the whole sky. We can look at maps of our small region of the sky. For example, around Rigel, that's the star, with an astral range of 20 angular degrees in the equatorial frame. So we see stars here. We see things like diffuse nebulas. We see the constellations, the lines of the constellations. We can, for example, zoom in. We are going to zoom in around this point.
You wrap it up, so it's about time to give me it up.
Yep. Okay. So that's zooming in around the star. Can change the background image. Or we can show the area around the galaxy. We don't have images of the galaxy, right? So we represent the galaxies with ellipses. We can do things like, for example, zooming around Jupiter. So let's do first zooming in. We go see Jupiter. That's Jupiter. And then at some point, we can now move this and we see the satellites of Jupiter, right? That's in days. We can compute multiple positions for Mars and then show them on a map, right? So, and we see the retrograde motion of Mars. Mars is currently there in red. That's the ecliptic plane. These are positions of Mars over a year or so. We can imitate solar eclipses. And here I have the solar eclipse of the observation by Eddington, right? In which he was able to measure deflection of the light by the sun.